Welcome to this explainer, where we're basically going to tear down the ultimate machine, the rocket engine, and see exactly how it manages to defy gravity. I mean, if you've ever watched a multi-ton cylinder of metal blast off a launch pad and wondered what's actually happening under the hood, well, you're absolutely in the right place. Today, we're unpacking the raw fundamentals of rocket propulsion.
Here's our flight plan for today. We'll hit 1. The physics of thrust, 2. Anatomy of a rocket, 3. The energy conversion process, 4. What makes rockets unique, 5. Types of rocket propulsion, and finally, 6. Why rocket science matters. Let's get right into it.
Starting off with Section 1, the physics of thrust, and how we actually go about defying Earth's gravity. Look, at the end of the day, it really all comes down to conservation of momentum and Newton's third law, action and reaction. The core concept here is honestly incredibly simple, even if the engineering to pull it off is mind-bogglingly complex. Basically, a rocket just throws mass out the back as fast as humanly possible to push itself forward. During operation, your fuel and oxidizer undergo this rapid combustion, which generates expanding gases that blast out of the nozzle at extreme velocities. That exhaust gas, that's your action, and the reaction force generated is the thrust that accelerates our rocket in the exact opposite direction. Moving on to Section 2, Anatomy of a Rocket. Let's actually build this ultimate machine piece by piece.
First things first, we need our raw materials, fuel, and an oxidizer. Now, because there's literally no air in space, rockets have to lug their own oxygen supply along for the ride. How we store all of this really depends on the system you're looking at. In solid rocket motors, the fuel and oxidizer are literally mixed together into a solid grain. In liquid rocket engines, they're kept in completely separate tanks. And in hybrid engines, we're actually combining a solid fuel with a liquid oxidizer. But what's really wild here is that these storage tanks aren't just, empty metal buckets. They are incredible feats of engineering all on their own. They have to be insanely lightweight while somehow withstanding immense internal pressures and, in the case of liquid systems, deeply cryogenic, bone-chilling temperatures.
Okay, next up, we've got to get those propellants out of the tanks and into the engine, and that is exactly what the feed system does. Whether it's pressure-fed or driven by these massively powerful turbo pumps or gas generator systems, the feed system is rushing those propellants into the engine at a highly regulated flow rate. And once they're in, well, highly reliable ignition systems have to spark the reaction. This could be an electrical spark, pyrotechnics, hypergolic liquids that just spontaneously combust the second they touch each other, or even experimental laser ignition. And trust me, reliable ignition is absolutely crucial here. When you're essentially lighting a controlled bomb, you really want a safe and predictable startup. So the propellants violently crash into the combustion chamber. This right here is where the chemical magic actually happens. The chamber's entire job is to rapidly mix that fuel and oxidizer together and maintain a stable combustion. By burning these chemicals, the chamber is kicking out massive amounts of thermal energy and extremely high-pressure gas. Just to give you a sense of how extreme this environment really is, this combustion generates gases at temperatures usually sitting somewhere between 2500 and 3500 Kelvin. Guys, that is hot enough to melt most metals. Because the chamber is dealing with these literally apocalyptic temperatures and pressures, engineers are forced to use exotic, super high-strength materials and design incredibly clever cooling systems just to keep the engine from completely melting itself into a puddle of slag. Now, once we've got that superheated, high-pressure gas, we have to actually harness it. Enter the convergent-divergent nozzle, often called the de Laval nozzle. This thing is genius. It chokes the gases right down to the speed of sound at its narrowest point, the throat, and then rapidly expands them as the bell flares out. This specific shape essentially acts as a massive accelerator, converting thermal energy straight into kinetic energy. It maximizes the exhaust velocity, which directly maximizes our thrust and seriously improves the overall efficiency of the whole system.
But hey, thrust without control is really just an explosion, right? To actually steer the vehicle, we rely on a thrust vector control, or TVC system. This setup slightly alters the direction of the exhaust plume to keep the rocket perfectly locked on its trajectory. Engineers pull this off by physically pivoting, or gimbaling, the entire nozzle, using jet vanes right inside the exhaust stream, injecting secondary fluids, or even dynamically throttling multiple engines at once. It's what gives us that pinpoint accuracy as the rocket is just tearing through the atmosphere.
Which brings us to Section 3, the energy conversion process, how we go from raw chemicals to actual thrust.
If you think about it, a rocket engine is fundamentally just a high-speed energy conversion machine. It flawlessly executes this rapid-fire chain reaction. Step 1, we start with stored chemical energy sitting in the propellants. Step 2, that energy explodes into intense thermal energy inside the combustion chamber. Step 3, that immediately builds into massive pressure energy. Step 4, as those gases are forced out through the nozzle, that pressure turns into the kinetic energy of exhaust gases hurtling away. And step 5, the end result is sheer mechanical thrust. The efficiency of this exact 5-step conversion is ultimately what dictates the performance of the entire rocket.
All right, Section 4, what makes rockets unique? Let's talk about some extreme engineering.
So, rockets operate totally differently than a car engine or a jet airliner. First off, they are completely independent of atmospheric oxygen. Because they carry both their fuel and oxidizer, they operate seamlessly out in the dead vacuum of space. Second, they generate exceptionally high thrust. I mean, they literally have to overpower the gravitational pull of an entire planet just to get off the launch pad. And third, they have surprisingly short burn durations. The main engines on a launch vehicle usually only run for a few minutes during ascent. After that incredibly violent, intense burn, the engines shut down and the spacecraft just coasts, totally governed by orbital mechanics.
But all of that incredible, awe-inspiring power comes at a very steep cost. Because these engines gulp down massive quantities of propellant in such a tiny window of time, the sheer weight of that fuel, the propellant mass, becomes the absolute dominant factor in designing any launch vehicle. To put it in perspective, most of a rocket's weight, while it's just sitting there on the pad, isn't the actual rocket structure or the payload, it's literally just the fuel required to lift itself up.
Let's move to Section 5, types of rocket propulsion. We're looking at chemical, electric, and nuclear systems.
Right now, the space industry relies heavily on two very contrasting technologies. On one side, we have chemical propulsion. This is your classic solid, liquid, or hybrid rocket. It generates thrust through violent exothermic chemical reactions. It gives us that massive brute force thrust we desperately need to escape Earth's gravity well. But on the other side, we have electric propulsion, things like ion or Hall effect thrusters. These accelerate electrically charged particles using electromagnetic forces. Now they have incredibly low thrust, sometimes equivalent to just the weight of a single piece of paper resting in your hand, but they boast absolutely massive efficiency. So that makes electric propulsion perfect for spacecraft that are already up in orbit or coasting out through deep space.
And then we have the true frontier, nuclear propulsion. These systems use nuclear energy as the primary power source, whether we're talking about nuclear thermal rockets or nuclear electric propulsion. Looking ahead, these systems offer tremendous, game-changing efficiency gains over our traditional chemical rockets, and they're widely considered a highly promising solution for our future long-duration missions.
Finally, Section 6, why rocket science matters and what this means for the future of spaceflight.
You know, mastering this level of heavy engineering is really what allows our modern society to function and expand. Rocket propulsion is the foundational technology behind deploying our global satellite networks, resupplying the space station, enabling human spaceflight, and pushing our probes further into the cosmos. Basically, every single time you check your GPS or look up a weather forecast on your phone, you are relying heavily on the success of these exact propulsion fundamentals we just talked about.
By fundamentally understanding how this machine works, from the chaos of the combustion chamber all the way down to the shape of the de Laval nozzle, engineers can keep pushing the boundaries of what's possible. The ongoing goals are clear: evaluate performance, select better propellants, and significantly boost our payload capacity. And perhaps most importantly, having a deep mastery of these systems is exactly what's driving today's drastic reduction in launch costs and paving the way for the rapid development of next-generation, fully reusable launch vehicles.
Which leaves us looking toward the horizon. We've seen how chemical engines have mastered the violent journey to Earth's orbit, and how electric engines quietly, efficiently push our probes through the void. But as we aim even further, we have to ask a big question. With chemical engines taking us to orbit, will nuclear propulsion be the ultimate technology that finally takes humanity to Mars and beyond? Well, thanks so much for joining me on this explainer today. I really hope you leave here with a much deeper appreciation for the magnificent, fire-breathing machines powering our journey into the stars.